Good morning. This is one of my favorite images. It's from Arthur Holmes, 1945. It wasn't originally in color. It's been colorized later. Arthur Holmes is mainly known for his work in radioactive decay and determining the age of the Earth. But he also dabbled a little bit in speculating about what's going on in Earth's interior. And you know, in geodynamics, we typically consider him the grandfather of geodynamics because he was one of the first, if not the first, to propose a mechanism for continental drift on the Earth's surface. Now, remember at this time, most respectable scientists did not believe in continental drift at all. They thought this was a crackpot idea. And one of the reasons they thought it was a crackpot idea is because nobody had proposed a mechanism for how it could occur. So it sounds cool having continents move around the Earth, but the thoughts then were that if continents moved around the Earth, they must have plowed through the ocean floor, and that, you know, could be quickly shown that that doesn't work out physically. So Arthur Holmes proposed that radioactivity in the Earth could provide the heat to make a heat engine in the mantle, and stresses due to that convection could act upon the surface and cause compression and tension and move stuff around. So for example, in this picture up here, here's a continent here. This is the lithosphere, oceans. And Arthur Holmes proposed that you could have upwelling in the convection cell, and that would create tension in that continental block. And you can have compression in the ocean areas, or you could have downwellings, and that could cause compression in the ocean areas. And that tension and compression could cause things to break apart at the surface. For example, you could create an ocean, and he was probably thinking about the Atlantic Ocean here, where you had tension underneath a continent, and you would create new oceanic floor. And where you have the compression, you could have lithosphere sinking down into the mantle, and you could form these deep trenches. Now, they didn't know about subduction zones then, but this is a pretty, looks like a subduction zone to me. This is 70 years old, and I think it's amazing how in that 70 years we've learned a lot about this surface area. So we know this much better. We understand the kinematics of plate tectonics and the different boundaries and how they work and their stresses and their strains and their velocities. But I have to confess, we still don't know. I mean, we're not really much better off in this area down here. In fact, here is a collection of cartoons, and most of these are modern day cartoons of different ideas of what we think is going on in the Earth's interior. So these are all, you can think of these all as different hypotheses. Here are a couple simple ones from introductory textbooks. This is a very popular one you would see in an introductory textbook now that shows and it's very simple to teach to introductory students that plate tectonics is part of a convection cell. So where you have upwellings, you have plates spreading apart, and where you have downwellings, you have slabs sinking back into the mantle. So this is very easy to teach. When I was a student, an undergraduate student, I was taught that this was how it is, this layered convection model, that you had convection in the upper mantle that was separate from convection in the lower mantle. And I remember as an undergraduate student, this is when I first became interested in geodynamics because I was very fascinated by something like this. And in particular, I was fascinated by the direction of the arrows. If you notice here, if the convection cells are set up such as things are rising here, and then you go into the upper layer, and things are rising here as well. So this system's thermally coupled. If the mantle has high viscosity, you wouldn't expect that. You would expect things to be viscously coupled, so you'd expect the convection directions in at least one of these layers to be opposite of the top. So I found that interesting as a student. But here are the models that you might see at AGU. These are the ones that we're throwing around now. And at first glance, they all look similar in the sense that they include lots of junk in the mantle, like different things. Like these are simple models, but these have a lot of compositional heterogeneity in them. And we think the Earth's mantle does have compositional heterogeneity in it at the large scale. The main thing we're debating about now, well, we're still debating about that, whether that's true. But if we assume that's true, one of the things we're debating about now is what dynamical form does that heterogeneity exist in? For example, is heterogeneity stable in the lower mantle, or is it rising and sinking, or is it breaking apart? There are lots of questions. And these are very important questions because each of these cartoons, even though they might look the same, they all imply a different style of dynamics, a different style of thermal-chemical convection, we call it, when we're dealing with thermal and chemical processes. But each one of these have fundamentally different consequences for many things that we want to understand about the Earth. One is the driving forces of mantle convection and plate tectonics. Each of these models would lead to a different set of drivers that is causing plate tectonics. Heat transport and thermal evolution is very much affected by which one of these models is occurring in the Earth's mantle. These all have different temperature structures and different changing temperature with time predictions, I guess you would say. Each of these have different implications for the chemical evolution and the cause of the difference in Morb and Oib trace chemistry. So Bill talked a little bit about those differences yesterday. So those are differences we see at the surface. What's causing them below? The geodynamo, the mantle is a boundary to the core, and each of these models would impose a different thermal boundary condition on the core, and it could influence the geodynamo. And finally, if plumes exist, which most of us think they do, their size, their temperature, their chemistry, where they come from, all depend on which one of these models that we assume. So I normally talk, well, first of all, let me, if I could put into categories the different things that we do in geodynamics, I could put them into three different categories. One is physics. So the mantle behaves as a fluid, and we understand the physics of fluids. And so part of geodynamics is working with this physics here, deriving the equations like Michael did yesterday. But then beyond that, we don't usually like to use the full equations. We like to make them simpler, and not just because they're easier to deal with, but because the simpler we make those equations, the more we can control our experiments that we perform. These are all very different aspects of geodynamics, actually, but they're complementary. Another aspect is the application, or the modeling. So once you understand the physics, only for the simplest of problems can you solve these physical problems by hand with paper and pencil. For any realistic problem, you need to solve these on a computer. And that's what I do, and Ming Ming is a student of mine, and he does the same thing. You can solve these equations on a computer, usually a cluster of some sort, and using parallel computing. And you can use either finite difference or finite element methods to solve these equations. Another way to tackle this physics is to scale the problem, and we'll talk a little bit more about that later, in such a way that you can perform an analog experiment in some kind of tank, in some kind of experimental setup. So instead of solving the equations, you're reproducing the system in some kind of laboratory experiment. And that's, geodynamicists typically you're either a computational geodynamicist or you're a laboratory geodynamicist. And sometimes people do both, but usually you're one or the other. Each of these require a different set of expertise skills that you develop through all of your grad school days and postdoc days. Finally, the fun stuff about geodynamics is the science. And that involves looking at observations, using those observations to come up with hypotheses. And those hypotheses usually are in the form of some kind of cartoon. One thing I can say is, cartoons are very useful, but they're often very wrong. And that's just because in our minds, we're flawed. When we start sketching things, we think fluids do things that they might not really do. So one thing geodynamics can do is help in the hypothesis development. So if somebody says, I have this idea, I think this stuff is doing this. People say this kind of stuff, like, I think the plume is doing this and that. Well, you can test that. You can use these equations, do some numerical modeling to see, would that ever happen? And oftentimes the answer is no. But sometimes Yes. And so geodynamics really helps to develop hypotheses. But these are just hypotheses. And ultimately what we want to get at is testing those hypotheses. And so geodynamics is useful for that in the sense that you can take a cartoon model like this, you can perform a calculation of it from it, and then you can, what I like to do is then come up with things that see what that model predicts that hasn't been observed yet. Like if I model this, and so I run some calculation, are there predictions I can make that then I can go to seismologists and say, if this is right, you should also see this. And I think that's when it becomes really interesting. My personal philosophy is that it's not very worthwhile to try to simulate the Earth. There's so many uncertainties. Modeling mantle convection is not like modeling automobile crash or something like that, where you know all of the finite element modeling of like bridges and stuff like that, where you know all of the parameters. We don't know many things. So we can't really simulate the Earth very well. And if we think we do, oftentimes we're fooling ourselves, and that simulation is very non-unique. That could be one of a million simulations. I think instead, my philosophy is I like to look at observations, come up with hypotheses, and create the most simple experiment possible. So think of geodynamics as an experimental tool, and just like a physics experiment, you want to get rid of as much complication as you can to test the hypothesis that you're trying to understand. So normally when I give a talk, I focus on this, and I sometimes pride myself on never showing an equation in any of the talks I give. Unfortunately for you guys, because I want to continue the theme of working through some of the physics here, most of the talk is going to be on the equations. And if there's time left, which there may not be, but if there is, then I want to talk a little bit more about this and the constraints that we have on mantle convection. So I must confess first, I've never done equations on PowerPoint before. Normally I do it on the board, but there are so many equations that it's not very efficient. Plus you guys don't have good writing areas. So plus having it on PowerPoint, you can download it and you'll have the equations. So this is kind of experimental in the sense of doing equations on PowerPoint. And I was up half the night entering these into Microsoft Equation Editor, and I'll never do this again. Like I thought, I had everything worked out, and I thought, okay, I'll just spend an hour to do this. No, it's horrible, actually. Okay, so I'm gonna start off from where Michael left off yesterday, and I want to talk about the three different conservation equations. And the goal here is to not just to show you a whole bunch of cool equations, but the goal is to familiarize yourselves with these equations and what we do with them, how we finesse them a little bit to turn them into a workable form. So when you see these in the literature someday, often you'll see them in different forms. One paper will show one form of equations, another paper will show a different form. They're the same equations really, but they might have different approximations or different setups. And if you've had some exposure to that, it's easier to deal with than if you haven't. So my goal is just to give you some exposure to this. Okay, conservation of mass. This is what Michael left with yesterday. One thing I like to do, well, first of all, conservation of mass, the rate of mass change in a volume equals the rate of mass entering the volume minus the rate of mass exiting the volume. And Michael derived this nicely. One thing I always like to do is to separate the independent variables from the dependent variables. In all of these equations, the independent variables are time and position, so x, y, and z, and time. Now, in some formulations, these will be r theta and phi, or if you're dealing with spherical geometry. Dependent variables for the conservation of mass are density. So density is a function of space and time. It's a scalar field. And v here is velocity, and that's also a function of space and time, and that's a vector field. Conservation of momentum. So if we were to derive this, we would just look at a volume, say the rate of momentum change per volume equals the rate of momentum entering the volume, or being advected into it, minus the rate of momentum advecting out of the volume, plus the force acting on the volume. And just like Michael showed yesterday, you get an equation like this. So here's how the velocity or the momentum is changing per time in a volume. Here's the momentum being advected in and out of that volume. It's related to some dot product here. Here's the divergence of the stress, as we saw yesterday, and the weight of the material. And again, the independent variables are the same, but the dependent variables, density, velocity again, stress. Now this is a tensor field, and it's at each point in space and time, you have a different tensor describing the stress, and gravitational acceleration, which is a vector field. Now just to highlight the stress a little bit, the stress tensor is just a fancy way to fully describe the stress state at a point. And so if you know the stress tensor, you can choose any direction, and once you choose that direction, you can calculate what the stress is on that surface. The notation we normally use for each component of the stress tensor is we have two subscripts. The first subscript is the normal to the plane that you're interested in. So in 3D space, if I choose a plane here, I take the normal to that. That is the direction described by A. Normally we do this in Cartesian coordinates. So if I have, so let's say this face right here, these are the different stress directions, the perpendicular stress directions on that face. That face, the normal, is in the x direction, so all of these things have x as their first subscript. The second subscript describes the direction which the stress is acting. Okay. And one thing to note, and this is very, very important, so if anyone is ever digging into these equations at a deep level here, the first thing you should always do is to look at pictures of the stress. And there are different conventions. Some textbooks, and I will use this convention where the stress is pointing. So positive stress means it's pointing away from the volume. You'll see oftentimes in other applications, this arrow will be opposite and stress will be directed inwards. That's very, very important to keep track of that. And pressure, so to make things really messy and give you headaches, when you're first doing this stuff, pressure is usually defined to have the opposite direction of the stress, so you always have to deal with that. Pressure is the average of the normal stresses on that volume. So the average is 1/3 times all of those diagonal terms in the stress tensor. And because by convention, we're choosing, I want to make pressure in the opposite direction, we put a minus sign there. So this is something you always need to keep track of. Look at your stress directions. If you're following someone else's derivations, look at the stress directions, look at the pressure directions. They are different from textbook to textbook to research paper to research paper, so it's very important. In fact, I almost made the mistake. I had a picture here. I just caught this about an hour ago. I had a picture here where the stresses were in the opposite direction, and I just caught it, and I changed this before I came in here. Because that could have caused some serious headaches for you guys if I would have posted this and then you relied on this for something. So even I make this mistake a lot. So by construction, so one thing we should always keep in mind is what are we doing versus what is the physics doing. This is all mathematics. This is what we are deciding to do this. We are constructing this pressure. Now, pressure does have some physical meaning, but for purposes right now, it's just a mathematical thing that we make up. And we can define a deviatoric stress. And so we make up this condition here that the real stress equals something called the deviatoric stress minus this pressure that we defined ourselves. And therefore, the deviatoric stress, by definition here, is just the stress plus, and that plus comes because of the different directions, pressure times the identity matrix. So I just want to quickly, Michael dealt with this yesterday, so I can quickly go through it. Once we do that, if we have divergence of the stress, and we can do some vector calculus here, the cool thing about that is that equals then the divergence of the deviatoric stress minus the gradient of some pressure. And it's kind of useful here to have this pressure term. And it's also useful to talk about deviatoric stresses because you could be in a situation where you have lots of stress in every direction, but that stress isn't different in each direction, so it's not causing any deformation. So it's not interesting then. Okay, so therefore here's another way of writing the conservation of momentum with that pressure term in there and with the deviatoric stress. So this is identical to what Michael had yesterday. Now finally, conservation of energy. This is the most difficult one. It usually takes me about 2 or 3 hours to derive this from scratch. So we certainly don't have the time to do that here. But if you want to derive the conservation of energy and at the deepest level, there are easier ways to do it. Usually when we do conservation of energy, we just think about it like, okay, heat must be coming in from this and going out due to that, and you can add things up. But if you want to derive it from a fundamental level, you need to use thermodynamics. And essentially to calculate the conservation of energy, you take the first law of thermodynamics here and take the time derivative of this. So we're looking at the rate of internal energy change in a volume equals the rate of heat transferred to the volume minus the rate of heat exiting the volume minus the work performed by the volume. And this is usually the messy thing to deal with when you're doing this derivation. So let's pretend like we just spent a few hours doing that derivation, and it is really ugly, at least how I do it. And maybe there's some tricks I don't know about. But this is what you get in the end. And even this is kind of a cheat, and I'll explain this in just a moment. So the conservation of energy. So this is the change in thermal energy per time in a volume. This is the thermal energy that's advected in or outside of that volume. This is thermal conduction. So heat flows or diffuses from hot to cold. And here's the minus of the heat flow here. And so this is opposite of divergence of the heat flow. This is the adiabatic term. So note here you have a change. This is material derivative. Michael introduced that yesterday. You have a change in pressure with time. And when things change pressure with time, they're expanding or contracting. And this causes things to adiabatically heat up. Well, cool down if they're expanding and heat up if they're contracting. Then you have this term here, and I'll explain what this vector calculus is in just a couple minutes. This is the viscous dissipation. So essentially this is the friction. So if you have material sliding past itself, then it creates heat due to friction. This is a lump sum of 1,000 other things we could add to this equation. So in this derivation here, we have to deal with entropy. And entropy changes due to changing temperature, pressure, and heat coming in. And all of those changes are incorporated in this derivation, how entropy changes for a homogeneous material undergoing changes in temperature and pressure. But in real life, there are many, many things that can cause changes of entropy. Chemical reactions are changes of entropy. Radioactive heat decay is change of entropy. Nuclear reactions change the entropy. If we all sat down here, we could probably make a list to fill up this whole board of all kinds of physical things that can change the entropy of a system. And so if I were a purist, I would have everything that we know, in physics here, following this. But usually we're not interested in lots of these different things that change the entropy. So I kind of like to have a trash can here. I call it S star, and that's all of the changes of entropy due to other things that we're not interested in. Yeah.
I guess I wonder if you want a temperature in front of that entropy term, a T, D, S.
Maybe I.
Thinking about your first law.
Maybe I did. Maybe I left that out. Okay. I'll check on that, and I'll.
So the garbage
I'll
can
fix
needs
that.
to be multiplied by temperature.
Yeah. That looks. That looks. Yeah.
Here in the momentum equation, first term on the left-hand side, first term on the left-hand side, the first term on the right-hand side. Assume rho is constant in order to take it outside the derivative sign, as well as the v.
These don't assume that yet. We're not assuming that yet. I can show you afterwards. So we're not using.
Then there should be another term.
I think it's all in there. Let's chat about this afterwards. I have notes on all of this stuff. I'm pretty sure that well, I know that no approximations have been made, and I'm pretty sure I didn't leave anything out here, but we can check that, and I'll fix that if that's the case. Okay, so I explained this entropy thing. So we have that trash can entropy term, and one thing that we often like to deal with in geodynamics is heat production. And in the Earth's mantle, heat production of uranium, thorium, and potassium are important. So we often just pull that out. And we say we know that causes changes of entropy, but how much heat does that produce? And that's the density times some thing, h. Well, we can define this any way we want to. You can get serious about it and do each of these elements separately and have them decay with time, or you can be really sloppy and just say, okay, I'm going to call all of that stuff h. That's how many watts per meter cubed, or watts per kilogram are being produced, and use that. So that's what we normally do in geodynamics. And so that's what I did here. So this is an example of pulling something out of here that's important for my problem, and I put it here. And I'll still leave this trash can. You'll notice somewhere during the lecture I'll just forget about that. We can always return to that later. Another thing that I don't do here, but it commonly comes up in geodynamics is phase changes. If you have a phase change from one material to the other, this included in here is the latent heat that's produced. Material changes. You have heat produced or absorbed when you undergo a phase change.
Include recrystallization in the different flow, or is that in the viscous dissipation? Does this term include recrystallization in the flow, or is that in the viscous dissipation? I haven't thought much about that, but I would think it's probably here, because if that's anything that can cause additional heat. I guess what occurs to me is that I guess there's a lot of work done in bending plates in subduction. I'm not sure how important it is elsewhere, but isn't that becomes really important then, doesn't it?
Usually then that's, I don't think so, because I think normally then that comes into here. In the momentum equation, you treat the material as elastic, or partially elastic, and I think that's where most of the physics. But I haven't thought much about that, so I don't know fully. Yeah.
You've said it before, the entropy change, you say it's both radioactive and nuclear, and the nuclear would be the absorptions of neutrons and alphas?
Yeah, I'm just saying everything that caused. I was being really sloppy there. Any physical process.
That was being very particular. I thought it was amazing if you're actually calculating that.
Oh, no, I'm not. This is a trash can that I don't touch with a 10-foot hole. But you can, right? So it depends how serious. If you wanted to model that stuff at a serious level, then you would dig out the physics related to that and then include the entropy change in there. Yeah, right.
Yeah, but it's not just the heat from the decay, but it's also the absorption of the neutrons and the alphas.
So all of that stuff you'd have to, work out some equation, change of entropy with time equals blah, 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 then pop that in there.
He gives values, he said, including everything but the neutrinos.
They take their energy away.
So I want to have just a couple explanations on the notation that I used. This strange term, which most people don't see. Most people don't ever see this in their lifetimes, but this is a weird term. This is a weird thing. Every time I see it, I have to pull out the books and figure it out, and usually I can't find it, and I have to work it out by hand a little bit. This is very simple, actually. This is a tensor acting on a tensor, so the gradient of a vector is a tensor, and it leads to a scalar. And if you work this out, this is what it really means. And so this is the viscous dissipation term. If you think about this in a qualitative way, what this is really saying is you have some surface, and there's some stress on that surface. And this is how much movement you have on that surface. So you can convince yourself that's the case if you start drawing some pictures and thinking about what these terms are. It's the movement on a surface of a certain stress. And you're looking at all different surfaces. Michael did a good job explaining this yesterday. Material derivative, so I don't really have to say much about it. Except material derivative can act on a vector, or it can act on a scalar. That's how you normally see it. But it can also act on a vector, and we'll see that here. And I imagine it can work on tensors too, and I don't see any reason why not. Okay, so in summary, still no approximations. These are the conservation equations that we have. I want to talk about these. The first one's pretty straightforward. I want to talk about some of these terms here. In the momentum equation, this term, we often call this the inertia term or the inertial term. This just, objects when they're in motion or at rest, they like to stay in motion or at rest. This is essentially what this term is. This next term here is the pressure term, or gradient of the pressure. Material, particularly fluids, like to flow from high pressure to low pressure, and that's controlled by this term here. This is the viscous dissipation term, but it can also apply to elastic processes too. We haven't defined what the stress is yet. We haven't defined this constitutive relationship. But this is often a resistant term here. This is friction. So things are moving, they produce friction, they resist motion. And finally, this is the weight of the material. And this is very important in convection problems. This is what drives the flow. It's lighter things will float, heavier things will sink, usually. So all of these things together, I always think the best way to think of all of these terms is to think of a garden hose. So if I have a garden hose, I screw it in into a spigot. The other end's open. And if I turn that hose on, what I'm doing is creating a pressure gradient, right? It's high pressure where the hose is plugged into the spigot. Is it spigot or spigot? It's so weird. I never like that word. There's high pressure there, and then where the end of the hose is that I'm holding, that's zero pressure. And so the reason water flows through that hose is it goes from high pressure to low pressure. This term is really dominating that. But once the water goes out of the hose, nothing's driving it anymore. There's no more pressure driving it. These terms kind of take over. So this is the inertia. So water comes out of the hose. It doesn't just plop to the ground. It keeps going, and that's because it has inertia. But then it eventually will fall to the ground, and that's because of its weight. Now, if I have a very viscous fluid, like if I tried to hook my hose up to a jar or to a keg of honey, the viscosity, this term will start playing a big role in resisting that inertia. So if I have honey coming out of my hose, it's not going to spray in the air. It's going to drip down, and that's because this friction is counteracting this inertia, and then this density can take over. So I always find whenever I want to think about all of these terms, I think of a garden hose and having different materials flow through that garden hose, and then I can think about which of these terms control that, the different observations associated with that. Okay, this energy equation here, this is the conduction term. This essentially controls the diffusion of heat from hot to cold. This is the adiabatic term that I already mentioned that. This is the viscous dissipation term, so the frictional heating. And this is the heat production term. And again, we can pull out any additional physics, anything that changes the entropy, we can pull that out as we need to. Okay, so we haven't made any approximations yet. So now what I want to do is work toward transforming these equations into a form or forms that we use in geodynamical modeling. And that involves three things: definition of a reference model, non-dimensionalization of variables, and approximations of physics and material parameters. So I want to cover these two things first, but this is probably the most important thing to deal with, actually. So reference model. Oftentimes in fluid systems, not always, but oftentimes, the parameters are pretty much fixed, and it's just little perturbations to those parameters, like perturbations of density, like small changes of density can drive flow, whereas the density of the entire system is pretty much constant, but a little change in density here can cause flow to happen. So it's very convenient to separate our variables into reference functions and perturbations to that reference function. Those perturbations are also functions. Yeah, so kind of, this happens all the time in all different things. And this is mainly a mathematical convenience. It'll make things easier to think about and easier to work with later on. So we can think of density as having a just split it into two pieces, a reference density that we define and some perturbation to that. One thing to note is that reference density can change as a function of space, but we're keeping it fixed with time, where the perturbation has this time in it. That's one key difference there. We can do the same thing with pressure. We have a reference pressure that's not a function of time, and a perturbation to that pressure which does have time, which is a function of time. Same with gravitational acceleration. This is not used much, only in special cases, but I have used this before. We'll talk more about that a little bit later. Gravity can be defined as a reference gravity plus perturbation to that reference gravity. And then finally, temperature, we can think of same thing. Reference temperature and perturbation to the temperature. Now, one extra condition we like to put on our reference model, so we can choose anything we want to. It's smart to choose something that's relevant. You don't want to choose some reference density model that's completely different from the Earth. You don't want to use a reference density for Neptune for Earth's mantle. You could, mathematically you could do that, but it just, it wastes, there's no point in doing that. It doesn't make this an easier thing to do then. So one thing we also like to do is we like to make sure that the pressure, the reference pressure, is self-consistent with the reference density and the reference gravity, and that it's self-consistently the hydrostatic pressure caused by these. And so if something's hydrostatic pressure, then the gradient of that hydrostatic pressure equals the density times the gravity. Okay, so we do this all the time in one dimensions for the Earth, like what is the pressure at a certain depth. It's the same mathematics here, except it's a little complicated because this G doesn't necessarily have to be in one direction. It can change with space. Okay, so once we have those reference models, we can plug them into our conservation equations, and oftentimes we can start simplifying things or Xing things out. So if we put reference density plus perturbation to density in this equation, then I'm going to leave it alone here. So sometimes I'm not going to do that. I'm just going to do it in places where I know that it's going to be convenient. So if we do that on the left-hand side, well, we know the reference density is not a function of time, so this goes to 0, and our conservation of mass now looks like this. It's the time change of density perturbation equals the divergence of this density times velocity. Conservation of momentum, we can do that too in a couple places. I'm going to leave it alone here, but I'm going to do it here with that gradient, and here with these two terms. So when you look at these, you'll have to look back a couple to see what this originally looked like. But essentially, that was density and that was gravity. Once we do that, and we can do a little bit of algebra here, this goes to 0. No, that's not right. This turns into this. So we saw that before. If it's hydrostatic, then it equals the density times gravity. That actually counteracts with this. So here's the plus density times g, and the minus. So we cross those terms out. So that's a convenient thing there. So we get rid of stuff here, and then our momentum equation looks like this, where essentially now we only have the gradient of the dynamic pressure. Actually, this perturbation to pressure is called the dynamic pressure. I didn't know. I think it's on the slide, but I didn't point that out. So we call this a special thing, dynamic pressure. So we got rid of the hydrostatic pressure here. Conservation of energy, we can plug in the reference model for pressure here. And if we look at this term, I don't like doing this stuff on the PowerPoint, but it's better on the board. But if we look at that term, we can see that we get this reference pressure time derivative, and that goes to 0 because there's no time here. So that term goes away. And so our energy equation now looks like this. So we just kind of modified our equations a little bit. We didn't really change anything, but we just changed how we view it by introducing those reference models. So in summary, here are the conservation equations, still no approximations, with a reference model included here. So basically, all of the things that are new are these perturbation terms with little hats, tildes on top. Okay, non-dimensionalization of variables. Now, the first question is why, and usually it's why with the exclamation mark first. Most students, including myself, just hated this in the beginning. It's like, why would you do that? You finally understand some physics of how fluid flows, and you understand those equations, and then you're just going to mess it all up by making things non-dimensional. Like, what does non-dimensional density mean? What's non-dimensional temperature mean? You know, your first reaction is, that doesn't make sense. That's not real. So most people are resistant to doing that in the beginning, and I was very much as well. Now I would never have it any other way. So the more you get used to it, the more you realize it's a good thing. So here are my reasons to why you would non-dimensionalize variables in these types of problems. One is to make the problem scalable. So once you non-dimensionalize everything, we're going to collect values or parameters of things together in such a way that we can see that we can scale things. For example, you can model Mantle convection in a fish tank, and people do this as long as we scale those parameters appropriately. Also, it leads to a non-dimensional collection of variables, or collections of variables, I should say, that can be used to characterize the system. And we'll see some of these. But common ones that you may have heard of are Rayleigh number. And if you dimensionalize things a slightly different way, instead of Rayleigh number, you'd get Reynolds number, dissipation number, buoyancy number, and there are many more. And these are just collections of constants that result from non-dimensionalizing the problem, but they have some physical meaning to them, and they're useful to relay that information. Like, oh, there's a Rayleigh number of 10 to the 6. My Mantle has a Rayleigh number of 10 to the 6. Well, my fish tank has 10 to the 6. Okay, we're in the same regime. Number 3, allows for a better understanding of parameter trade-offs. So once you do that non-dimensionalization and you have these numbers like Rayleigh number, you can understand how if you change one parameter, how it's equivalent to changing another. For example, for Mantle convection, if you double the density and the viscosity, if you double both of those, the system will remain unchanged. It will look the same. Those doublings cancel each other out. Also, if you double the density, that's equivalent to having the viscosity. So you can start to play those kind of games, and they become very useful. It becomes very useful when you're comparing models to be able to do this. Oh, and finally, numbers are closer to unity. So if you didn't non-dimensionalize things, you might choose to use SI units, and these are all over the place. Like, you might have 1,000,000 meters, and you might have temperature in kelvins. You have all of these different parameters. They have different magnitudes of values. And, it can be torture if you're working out that stuff. But, the main reason it's not great is because computers, and also if you're doing hand calculations too, we have a limited number of significant digits that we're dealing with. So if you're adding and multiplying things that are in grossly different scales, different magnitudes, then you increase the chance for losing some stuff in those significant digits. So when you non-dimensionalize things, all of the numbers are more similar to each other than they were before. Like temperature goes from 0 to 1, density is 1, viscosity is 1, on average. So you're dealing with things that are similar to each other. Yeah, and believe me, it gets easier. It's easier to work with it after you've experienced it a while, but in the beginning, it's kind of torture. So there are many different ways to non-dimensionalize a system. And the trick is that, and this is very important for students to understand, is there is no magic here. These are just mathematical transformations that we make up and we apply. And it might seem like magic because you look at this and be like, why would I choose these things? Well, people that have been doing this before us have thought about this, and they, maybe through some trial or error, or maybe some of them are really smart, they came up with these things before and told us like these are the good things to use. So, and that's, very valuable. So for thermal convection problems, but again, no magic. Like, we define these things. And so you need to have a little cheat sheet. And every geodynamicist has their own little cheat sheet and there are 2 more slides of all of these. I'm just going to go through quickly. We all have our cheat sheets here, and we have to even I have to refer to the cheat sheet often to non-dimensionalize something. So basically, I'm going to show a few slides of these things. I'm not going to go through each equation. But I basically want to say the thing on the left is the function. So this is the real function, like density. And the thing on the right, we have the function as well, but I put a prime on it. And that prime indicates that it's non-dimensional units. And it can have non-dimensional units because we pull out some reference value. In this case, this rho 0. So if I have a density field, let's say my density is 3,000 in my model, and it stays 3,000. I can say I'm going to choose a reference density of 3,000, and then all of a sudden my non-dimensional density just becomes 1, and I have this 3,000 thing in front of it. So that applies to all of these equations, and sometimes we try to be clever and come up with collections of terms that will be useful later on. That's why we have all of these three things here. There's no special thing about this except that it will be useful later on. The one thing we have to make sure, though, is that these collection of terms have to have to have dimensions equivalent to the original function. We have to make sure that dimensions are consistent. So we do this for all of the parameters. Do it for each one. So here are my cheat sheets. And here's the one I always have to refer to, this heat production. I always forget this one. Okay, so once we do that, so that's just a lot of hard work, actually. And I redid all of that last night just to make sure the equations were okay, and it took me a long time with paper and pencil. But once you do all of that non-dimensionalization, then you can do some algebra and start collecting. So you'll have all of these ugly terms all over the place. You can start canceling terms and moving terms over. So I did all of the algebra, and I didn't show it here, but I did it on a piece of paper, and then here are the results after doing all of that messy algebra. Now, one thing that will be, so first thing I want to discuss, and this usually stresses some people out, is now that I've non-dimensionalized, now I'm dropping all of those primes. Remember here, we have the density, the pressure equals some stuff times non-dimensional pressure, but this non-dimensional pressure is P prime. Well, now just because I'm too lazy to write primes everywhere, taking all of the primes out. So it's up, and we all do this in geodynamics, and it causes a lot of stress sometimes because you'll see the dimensional equations, and then you'll see the non-dimensional equations. The equations look different because you did this non-dimensionalization, but they took all of the primes out, and so you have to read the text where primes have been removed or something like that, and you have to know that ahead of time. So really, this is like density perturbation prime. This is velocity prime. So we have primes everywhere, and I just took them out, and it's just understood now that all of the parameters, or all of the variables, I should say, all of the variables are non-dimensional, and the only things that have dimensions are these parameters that we use to non-dimensionalize everything. So if that didn't make sense, please talk to me afterwards. This is one of the more confusing things in working with geodynamics, but it becomes easy after you have some experience. One thing I wanted to point out, whoops, it went the wrong way, that people often make this mistake in the beginning. When you do non-dimensionalization, you also have to non-dimensionalize your calculus operators. For example, the gradient, or the del, is equal to, or nabla, I guess is what's called, is 1 over some length scale. So h is the length scale. In Mantle convection, h is usually mantle thickness. And then you have the non-dimensional calculus operators. Same with the material derivative. So your calculus has to be non-dimensionalized too, and that's kind of a weird thing to wrap your head around. Okay, so once we do that, we have something that looks like this. So all of the primes are gone, still no approximations, but now we have these collections of parameters. Now we get to choose what these parameters are. Remember those transformations, there was no magic, we made them up. So we can choose what rho 0 is, kappa 0. So kappa is thermal diffusivity. We can choose eta 0. Eta is viscosity. We can choose what that viscosity is. Now to be useful, we will choose values that are representative of the system that we're dealing with. So if I'm doing this, I don't want to choose a viscosity of water for this value when I'm trying to understand mantle convection. I want to choose a viscosity relevant to mantle convection. I can choose any viscosity I want to, but in order to become useful, for this whole thing to be useful, I need to choose values that are relevant to the Earth. Okay, so these are the mass equation, momentum equation, and the energy equation. But what I want to do is now introduce, you saw I collected variables together. We can now talk about those collection of terms. So one collection of terms that we saw in those equations were these guys here. And we call that collection of numbers, we call that the Rayleigh number. Now, how relevant Rayleigh number is to our model depends on how well we chose these numbers. If I just chose some oddball numbers here, then my Rayleigh number doesn't mean anything. Just as an aside, one common problem in geodynamics is non-geodynamicists often think this Rayleigh number has specific meaning. In reality, it can have specific meaning, but it doesn't have to. It depends on how you've made these choices here of these numbers. So it has meaning if you've done it a certain way, I should say. And here's another collection of terms that we call the dissipation number. And here's another collection of terms that we call the Prandtl number. So in each of these have some physical meaning to them. Rayleigh number represents the how well things convect. Dissipation number, it's hard to really pin some deep meaning to that, but it controls how adiabatic expansion and or how adiabatic heating and cooling work and how viscous dissipation works. Prandtl number is related to the inertia of the system, so we'll talk about that in a minute or so. So once I've introduced those, I can turn here's the summary of equations again, where I've introduced those terms, Rayleigh number, dissipation number, Prandtl number. So those are just collections of those terms. Okay, so now we're nearing the end here. And I want to talk about the different approximations appropriate for Mantle convection modeling. So those equations I just showed are representative for any type of modeling you want to do, whether it's stars or supernova explosions or convection on Earth or convection for gas giants. It doesn't matter. But now I want to start approximating these equations to look more like what we can use for Mantle convection. The first assumption that's often made is we say that this change of density perturbation with time equals 0. And the justification for that is that this is mainly important if your system has shock waves in it. And fluid dynamics usually only has shock waves in it if the convective velocities are in the same order of as the speed of sound. So if you're doing supernova explosions, you wouldn't want to make this approximation, I imagine. But for Mantle convection, convective velocity, centimeters per year, is much, much slower than sound waves, which are essentially P waves in the mantle, which are kilometers per second. So if we make that assumption, our conservation of mass becomes very simple. It's just this divergence equals 0. We call this the anelastic liquid approximation. The next approximation we make is called the infinite Prandtl number approximation. I want to first demonstrate this. This is a neat little cartoon I got from, I think, Wikipedia. But it shows two. They should put them side by side. It's kind of distracting having one above the other. But these are two different fluids with two different viscosities. This is water. We're very used to this kind of motion, where this water is falling down under its weight. So that's the buoyancy term. And then once it falls down, it still has momentum. There's a lot of momentum in that water, and that momentum keeps splashing that water around. And we're all familiar with that. If you stir a pot of water and take your hand out, so you no more force on it, the water is still going to stir around in that pot. And that's just due to the inertia, the momentum. If you have a very viscous fluid, all of your momentum is being dissipated or diffused by friction very quickly. So if something drops due to its weight and then it settles, well, that momentum has been dissipated. So you don't have it splashing around. So the same thing if I take a jar of honey and stir it around with my finger. Once I take my finger out, the honey is not still stirring around. It stops, and that's because of high viscosity that's diffusing that momentum. So this Prandtl number was in front of our inertia terms in the momentum equation. In fact, we had 1 over Prandtl number. And if we apply some typical values for the Earth, like a viscosity of 10 to the 20 Pascal seconds, a thermal diffusivity of 10 to the minus 6 meters squared per second, and a density for the Earth around 4,000 kilograms per meter cubed, we get a Prandtl number of around 10 to the 22. Therefore, 1 over, and I'm being really sloppy here, but 1 over Prandtl number is very small then. And I guess if I were less sloppy, I would have to compare that to the terms on the other side. But let's say I already did that comparison, and I find that this is 1 over Prandtl number is very small compared to everything else in the momentum equation. So I can evaluate, kind of like Michael did yesterday looking at terms. You can do that. You can evaluate what the size of each of these things should be for Earth-like problems, and you would find that this term is almost 0 here because of this 1 over Prandtl number. And so we can take that out, and again, we call that the infinite Prandtl number approximation. This is not valid if you're studying fluid dynamics of the outer core of the Earth, but if you're, although I think some people do take it out as an approximation, is that right?
Yeah, that term's probably 10 to the minus 7, so it's not that, it's pretty small.
Okay. For the outer core. So it can be important for that. But for the mantle, this is not important at all, and we never use that. And so that's, if you're ever digging through the literature, one thing you should keep in mind is when you're looking at your equations, does it have these inertial terms, or this inertial term or not? And whether it does or doesn't depends on this Prandtl number. Okay, another assumption. I don't really want to call this an approximation, but for most problems, we don't care about perturbations to the gravity. For Earth, we think, okay, we understand the gravitational potential, so we know the gravitational field that's fixed. Now let's model it. But if we wanted to get picky, we would realize that when you have convection, the convection is affecting the gravitational field. Dense slabs are perturbing the gravitational field. Hot plumes are perturbing the gravitational field. What really perturbs the gravitational field is when that convection changes the boundaries. So if you're causing dynamic topography on the top, well, that's a pretty big perturbation to the gravity field. Same thing if you perturb the core mantle boundary. Now, there are some studies, and I have done this in the past. A former graduate student of mine, Teresa Lasick, the whole point of her, one of the main points of her work was to investigate this part of the equation here. She found it wasn't really that important for most problems. But there are times when you want to look at the perturbation to gravity. But for most problems, most experiments that you're dealing with, this is just a trivial complication. Yep.
It seems to me that one place that might be interesting is because the gravity is resisted by a centrifugal force, that you might get some polarization of convection, right? I mean, in principle, we seem, for example, to have plumes concentrated around the equator and not at the poles, and I'm wondering.
Yeah, so that
comes into
that's a good question. For mantle convection, that doesn't seem to be a big player. So a couple things. One is when you look at the momentum equation, because we're taking out the hydrostatic term, that gets rid of a lot of complications right there. But that's kind of a side point. But that doesn't seem to be a big problem. And in fact, but if we wanted to include that kind of stuff in this modeling, we wouldn't include it as a gravitational perturbation. I would include it in my reference gravity. You couldn't include that kind of motion as a reference gravity. So it doesn't have to be perturbation. This is really for time-dependent things where the convection is changing. You could. You can add anything you want to here, but it would be best to always just include that here. So you can still make this approximation and study those things. Okay, so this really isn't an approximation as much as just something we leave out most of the time. You can always put it back in if you want to study we call that self-gravitation when convection is perturbing the gravitational field. Okay, so now, this is like the umpteenth summary here, but I think it's useful to have all of these summaries with a description of what has been done to these equations. So here are the equations again with approximations listed. Anelastic liquid approximation, we call that ALA. Infinite Prandtl number approximation, static gravitational field. This is what the equations look like. So they're getting a little bit simpler. The next set of assumptions, or the next level of assumption we can make, is to say that the dynamic pressure does not contribute to density perturbations. So this is a more subtle approximation here, but typically a density perturbation can be the result of temperature, composition, and also the dynamic pressure. So if I have a material here and its density is different from the reference density, well, dynamic pressure coming in or pushing on it can actually compress it a little bit and change its density. So the truncated liquid, anelastic liquid approximation is just saying, you know what, this is not really a big player. These are the main players. Temperature and composition are the main things that control the density. So we neglect that. Also, from the energy equation, this approximation says the material derivative of this dynamic pressure is negligible compared to everything else. So then this term can be thrown away. So we have these are our adiabatic terms here. So these are both adiabatic terms. This is essentially the adiabat on the reference system, and this is the adiabatic effects on the perturbation to the pressure. So this is much smaller than this usually, so we can get rid of that. So now that summary, the TALA, the truncated anelastic liquid approximation, an infinite Prandtl number, static gravitational field, this is what the equations look like. Now in geodynamics, we typically go a little bit further than that. The next level of approximation is called the extended Boussinesq approximation. And in this approximation, we say density everywhere is constant, except for density perturbations in the momentum equation. Now, we can't have it constant. We can't have density constant everywhere, else we would never get any convection. Convection relies upon density differences. So we need to allow density perturbations somewhere. And that goes into that momentum equation. But we say everywhere else, let's just call the density equals to 1. Remember, these are non-dimensional things, so let's just call it 1 everywhere. And you do that, and the main consequence is it turns the material, or makes the material incompressible. So the continuity equation, or the conservation of mass, is greatly simplified. And you start simplifying a lot of the other terms that we had. And so now the summary, with the extended Boussinesq approximation, the equations look like this. So I took all of those density terms out, except for this density perturbation that needs to go right here. But there were densities in here, and I took them all out. I said they equal to 1. And then finally, the last approximation is called the Boussinesq approximation. And here we say we neglect all terms that have the dissipation number. So essentially, we're neglecting viscous dissipation, adiabatic heating, and cooling. We also make the specific heat, the thermal expansivity, and the thermal conductivity. We say those are constant. Now, up until now, these could be variable functions. Usually people don't treat them as variable functions because these are the least of our problems, of our uncertainties, I should say. And so we usually don't get too serious about these functional forms when we have no idea what the viscosity is, for example. Yeah. So, yeah, they can be. So these things are important for the lower mantle. And so it all depends on the experiment that we are dealing with. If our goal is to understand how thermodynamics affects certain things in the lower mantle, we certainly wouldn't want to make that approximation, and we would want to look at those things. Oftentimes, so these are still included, the thermal expansivity, thermal conductivity. It's just we're taking away the spatial function of it. We can still try different values, and usually that becomes, with all of the uncertainties in there, it's better to say, let's try these 5 different thermal conductivities than to say, let's try these specific thermal conductivity curves. But again, it depends on what experiment are we trying to do, what question are we trying to answer.
Is it possible for you to give some rules of thumb for the non-geodynamicist? If I read a paper and they say, oh, we're going to make the Boussinesq approximation, should I be thinking, I have to keep this caveat in the back of my head, and these might be the problems or outcomes that are affected by making that approximation? For example, as a geochemist, if I read in a paper that they've, say, filtered the data by the MgO content, as a geochemist, I immediately start thinking, okay, these are going to be the consequences of that filtering, and this is what I should be watching out for. This might be what was neglected by making that filter, putting that filter on the data. But as a geochemist, I don't have a big list of rules of thumb or things that I worry about when I read I just kind of trust the geodynamicist to have done it right.
So I guess we all do this.
When I read, we've made the Bruce-Nesca, should I be thinking, oh, it might not work for the lower mantle then?
Yeah. So we all deal with this. Like I used to trust seismologists until I started working with one next door. Now I don't even bother asking Edgar Narrow questions anymore about.
Maybe you mentioned it, and maybe I just spaced out for a minute. But I haven't heard you say rotation at any time.
No. So, okay, let me get to this question, and then that's a good question about rotation. Okay, first of all, I guess that's the same in every field. So, I guess one of my goals here with this is to introduce non-geodynamicists to these different approximations so you can start to look at them. As for rules of thumb, I guess take a copy of this PowerPoint with you, and if you ever encounter it, look at the things that each approximation has removed, and just think about the physics what physics did we remove? And I think that's the best I can tell you for rules of thumb, is to just be familiar with what things are taken out of each approximation, and be careful that the experiment that you're doing doesn't rely on those physics. There's never a clear...
Another way you could say it is, often it's an issue of scale height, right? People talk about how much does density change as you go through depth. And if the density variation is small, a small number of scale heights, then Bruce-Nesca is probably okay. I think in the mantle it's not too bad, right? It's maybe a factor of 60% more than the scale height or less than the scale height. So it's a reasonable approximation. In the core, it's actually not such a good It's not such a good approximation in the core, but it's a pretty good approximation in the mantle. The issue is really scale. The issue is scale height. The issue is scale height. So when you take a parcel of material from the bottom and you take it to the top, how many e-folding distances is that? Is it less than 1 or is it more than 1? If it's more than 1, then the Bruce-Nesca's got a problem. But if it's less, then it's probably okay.
Yeah, I think that's absolutely right. And then, different experiments might have different, like thermodynamics that you may be interested in as well. I guess I would always be familiar with those raw equations that had no approximations. So if you're trying to do this, just be familiar with that raw physics is and the equation that the person's using. And it's not straightforward. If this is the first time you're looking at this, it seems kind of foreign. But if you're used to it a bit, you can start to see what things have been taken out, and is that appropriate for the experiment that this person is doing. But there are no simple rules of thumb. You have to think about it a little bit. Now, going to that rotation.
I was just going to add to something that Bruce said, which I think is relevant, which is that some of the things that vary, some of the parameters vary exponentially, like viscosity, of course, varies exponentially with temperature. And some of the things that we're talking about vary only a very small amount over the entire mantle. And so, you're safer in some sense if you have to take some of these approximations, using those that don't, where the quantities are not varying exponentially with one of your free variables. So that's another. I think that basically echoes what Bruce just said.
So I want to quickly get to this rotation thing that Barbara asked about. Yeah. Oh, sorry.
Maybe we should point out at least a few things that the Bruce-Nesca approximation really changes in these models. At least the type of, for geochemists, often plumes are quite a big thing. And if you put out the compressibility and the adiabatic heating terms in there, then you will get in tendency you will have hotter temperature in plumes because they don't cool faster than the rest of the mantle as they would in an adiabatic thing. So you usually get like plume temperatures that are maybe 100, 150 kelvins hotter than you would expect in the real mantle. You would probably want to, if you would want to look at the excess temperature of these plumes, you would probably not want to use the Bruce-Nesca approximation. And for example, if you have a constant thermal expansivity over the mantle, which is likely to change by a factor of 4 in the real Earth, you would overestimate the driving force of your convection by a factor of 4. So this is something you might want to keep in mind if you have the simplest of all approximations in these kinds.
But I want to highlight that, what I think the dangers of simulating the Earth are. I mean, let's say I want to simulate the Earth, I can start including all of these additional physics, but with each of those additions comes a lot of additional uncertainty, and my model's becoming more realistic in a sense, but it's not becoming more realistic because it's introducing more uncertainty. I mean, there's some questions that I think absolutely the plume was a good one. If your goal is to what is the temperature of the plume, that's something people ask me all the time. What's the temperature of a plume? I say, we don't know. And even if I did the extended Boussinesq approximation or the ALA or TALA, I still wouldn't know any better than I did before.
Essentially because we don't know the temperature of the core Mantle boundary.
Yeah.
Mostly. Yeah.
So sometimes you can fall into a trap of trying to include more physics, but it's not going to help you answer the question anymore. Yeah.
Can I get in before? Can I get in before Bill?
Timo, who's next?
So in terms of the things that, is this even louder? Can we talk? Okay. In terms of the things that we don't know or we do know, it's ironic because we probably know the density change, throughout the mantle the best in terms of the mineral physics, right? I mean, these are the,
So the reference density.
The reference density, right. Those are the things that we can measure and we kind of have a good handle on. But it's the other things like the thermal conductivity and even arguably the thermal expansivity that's, and other things that are much less known. But, if you say, your density is just 1 and forget about it, but there's a lot of people in this room, myself included, that try to measure those changes throughout the mantle, and it's a little sad, right? It's like, but we worked so hard, but then you're just going to say it doesn't matter anyway.
Well, you're not just working for us. So.
Sure. But in this approximation, when you say it's incompressible, where it's it's just an incompressible fluid.
Again, I just want to highlight again, it all depends on the type of problems that you're trying to deal with. There may be some scientific questions where that becomes absolutely critical to do that, and then I would need to include that. So, people have different philosophies, but again, my philosophy is geodynamics is best used as an experiment. You have a scientific question, you have a hypothesis. How can we set up an experiment to answer that? And some experiments involve a lot more complicated physics than others. So it shouldn't make you too sad. I mean, there are questions that yeah. But I just want to make a quick point. When I was talking about the non-dimensionalization, if you look at the Rayleigh number, which largely controls the vigor of convection, so Rayleigh number, one thing that it has on top is, like the thermal expansivity, and one thing that it has on the bottom is the viscosity. So if this is uncertain by a factor of 2, 3, that's nothing compared to the uncertainty I have in this viscosity, which I don't know for orders of magnitude, plus or minus orders of magnitude. So I never stress out about I don't know what the thermal expansivity is in detail, because I'm always worried about this viscosity term. This is the one that always gets me the most. That's the one we don't have any good constraints on. Even if mineral physics told us with certainty, like these are the best viscosity formulations for all of these minerals in the Earth, we still wouldn't know what the viscosity is because it's highly dependent on the grain size, which we don't know. So this is always the problem that I'm dealing with. Oops.
Though you don't know them precisely, the power of these numerical models is that you can put ranges on how their behavior would be. If you're at a lower bound or upper bound.
Yeah. So that's what we do. Like for every geodynamical calculation you might see in a paper, there were probably 100 done that's exploring the range. So it's something we have to do for almost everything we do. I would say 100 is not an exaggeration. Wouldn't you say, Ming Ming, for each? Probably, maybe more for Ming Ming. Yeah. But yeah. Okay, going back to that rotation quickly, and then I think I only have one more slide after this, but going after that rotation, that's a good question. So here's the momentum equation. When the Earth rotates, it changes the boundary a little bit. So a lot of that rotation is actually canceled out by the change in shape for the Earth's mantle. and for the viscosities that we're dealing with. So it's not really a big player. But if we were doing core convection, we would certainly want to apply the rotating. This assumes a fixed coordinate system x, y, z. We'd want to just apply the transformations to a rotating coordinate system. Physics should remain the same, but it's going to look a little bit different with those, those rotational terms in there.
So that's valid for the present mantle. But if you had a magma ocean, maybe.
Yeah. So that was probably important for that. So it's the lower the viscosity is, the more important it certainly is, and the faster convective motions are. So it would be. In fact, I just saw a talk by Uli Hansen at CIG, I think it was, Louise, right? Uli talked about magma ocean type stuff, and he did rotation. And so people are including that. And I saw another talk recently, I forget by who. But yeah, it's important to include that when you're. Okay, so I think this is the last slide. So the Boussinesq approximation, for most problems, most simple scientific questions that you're trying to answer, these are the equations we use. Now, again, if there are any problems where we are more interested in the temperature of things, we might use the extended Boussinesq, because then we have some of those thermodynamic properties in there. But for most mechanical type questions, these equations serve us well, and they're simple enough. So, this took a lot longer than I thought, but I have like an additional few slides, but I'm just going to just mention them. I'm not going to go through them. These equations, I've left this density term here, this density perturbation term, and the stress term. I left those kind of like open-ended here. Now, depending on the specific application, you're going to plug something in for this and plug something in for that. And Michael talked a bit about this one yesterday. And so this is when now you're really specifying a problem at hand. And for Mantle convection, we usually say, okay, this is a viscous problem. The Earth is a fluid. There are no elastic things. And you relate the stress to some changes in velocities and viscosities. And the different approximations will do things. This term here is mainly important for shock waves, and so you can refer to this later, but this is usually what we use for the stress. And then density, the same thing. So the different approximations will have slightly different forms of the density. And you can include your additional physics if you want to do that. So I guess I'll just stop right there. And then I actually had a whole other scientific aspect of the talk, but we'll save that for another time.
Questions? Where was it that we lost our messy entropy term? In which stage of all this?
When I was doing the nondimensionalization, I didn't want to deal with it. So I should have pointed it out. Yeah, I just threw it away. Well, let me just add to that. So that's something, if you wanted to add some of that additional physics, you would want to do that before the nondimensionalization and then do the nondimensionalization.
So when I was seeing your approximations, I had the same sort of unease that Liz highlighted. And in fact, I was reflecting for a while, particularly on the issue where they were talking about the transfer of heat from the core mantle boundary to the surface, and particularly the historical evolution of the thought about that, and particularly some of the ideas that come up with CZ in his studies, which would modify it. And I just wonder, at some level, I trust your field, but I also worry that you go, well, have you oversimplified it?
Yeah, I think that's a valid worry. So
and
you should be skeptical of
where are you
modelers.
worried? Where are you worried when we say we have this transfer of heat from the core mantle boundary? We can parameterize it as X number of terawatts, but we realize that it's losing heat through this and that process. Where are you worried?
So my worries, or let's say my interests in that regard, of course, relate to the cause of the LLSVPs. And those will dramatically affect the heat flow coming out of the core. If you just have isochemical convection, your heat flow coming out of the core will be very different than if you had thermochemical piles at the base.
Maybe for some of the students, you might explain what we're really talking about in terms of actually getting a budget.
Okay, so in terms of getting a budget, I don't think I did a budget type thing here.
Oh, so trace element
diagram. Yeah. So, I guess I don't have a good figure, but let me just say this. So, just a quick thing. In the lowermost mantle, this is tomography of the lowermost mantle. We have these large regions beneath Africa and the Pacific that are lower than average seismic velocities. And these, I'd say the entire solid Earth community is kind of interested in understanding what these things are. Are they like thermal plumes? Are they compositional reservoirs? If they are compositional reservoirs, are they sitting there for long times, or are they kind of being advected in and advected out? And the answer to that question, so there are many different hypotheses, and this is a great cartoon. It's well over 10 years old now that Paul Tackley put together that kind of tries to satisfy the geochemistry by just proposing all different ideas of what could be happening in the Earth's mantle in terms of compositional heterogeneity. And we think that the LLSVPs, or we hypothesize that they could be caused by just these piles of material in the lowermost mantle. Now, once each of these models here have different consequences for how heat can get out of the core and into the mantle. If you have piles in the lowermost mantle, heat, well, these have a very high temperature, so your heat flow from the core into the pile is actually kind of small. Most of your heat flow is going into slabs. But these are very big reservoirs for heat. I guess the answer to your question, I could go on with lots of different, it could turn into a long discussion. But there are lots of different ways in which our understanding of the heat budget is perturbed by the reference model that we assume. Also, if you trust buoyancy fluxes from plumes, we often look at buoyancy fluxes from plumes and assume that there's some measure of heat coming out of the core. But if this model is correct, no, it's heat coming out of a pile, not the core. So there are probably many different avenues that we could discuss how the heat flow coming out of the core is dramatically affected. There's a geodynamicist named Takashi Nakagawa. He's worked on this a lot, and he's good, and he's pretty honest about what the models can and can't say. And so he would be the best source to look into how these models can affect the thermal evolution of the core. And it's pretty dramatic, actually. So that didn't directly answer your question, but it is.
This family of cartoons helps us to understand the context of the statement that people are making about the heat from plumes.
Yeah. Yep.
Hey, Alan. So I have a question about what you just said when you were pointing to the panel E. And you said, well, if we use the heat flux estimated from the plumes, that might only represent the heat coming out of the pile in that particular cartoon. But if you have a high core heat flux, how would you get rid of it without forming other plumes that are actually rooted in that kind of a drawing, right?
So that's a good question, and we've looked at this a little bit. So most of that heat, if you have a system like this, most of the heat coming out of the core is going right into these slabs, warming up slabs.
So even the really high heat flow? Even the really high heat flow?
High heat flow is highest. If you put a cold slab on the core mantle boundary, that's where you have the smallest.
But is there enough slabs to take out whatever they want now, like 17 terawatts of...
Wait, what was the first part of that question?
Sorry. You're trying to get rid of huge heat fluxes in the latest kind of estimates of core heat flux, right? We're talking about, 15, 13. Well, it depends who you talk to, right? But huge numbers of heat huge quantities of heat. So are there enough slabs, and is there enough kind of circulation of slabs down to the lower mantle to get that much heat out without us observing any plumes?
So that's a good. So the real answer is we don't know. I would say for viscosities, we typically assume in mantle convection models, most of those slabs are fine getting heat out. You don't get plumes forming. But as you start using what may be more realistic viscosity, temperature dependencies of viscosity, you could have little plumelets forming under slabs. And some models have shown such a thing. But this really becomes a viscosity dependent structure. But my first, so we don't know the answer to your question, but I would guess that slabs don't have any difficulty getting that kind of heat out of the core. I wouldn't consider it a problem.
Well, there are 6 cartoons, and only in one of them you don't have slabs going straight into the lower mantle. On the other hand, we know that in terms of slabs becoming stagnant at 650 or above transition zone, it's actually fairly strong evidence for it.
So this is interesting. I want to make a point here. Like, this is something I'm very interested in, actually. But we see a snapshot of today's slab today, and I actually have a picture of that. We don't, just from the snapshot, so I guess here's some. Just from the snapshot, we don't know that it's stagnant, right? That's the picture in time that we're seeing. We have no evidence that this is stuck here, but it could be. We just don't know. And in mantle, I can say one thing. In mantle convection calculations, it's very common to see slabs looking like this for short periods of time, but they're not stagnant at all. It's just taking a picture of time. Slabs don't always just go straight down in a fluid dynamical calculation. But we don't know.
When I have stagnant, obviously, could be anything, but there are many subduction zones where this actually happens and can continue for like 2,000 kilometers.
Yeah.
So you wouldn't still, stagnant doesn't mean forever, but for long enough that 2,000 kilometers of subduction, is hidden there. So all I was trying to say that this actually assemblage of geochemical models or models of the mantle does not quite have the breadth of different models that you could construct, even if these slabs propagate laterally and are trapped in quotes because it could be incorporate other models.
Yeah.
So it's not the only model that you don't have exchange of the material between upper and lower mantle.
Yeah, I agree. I mean, there are lots of. I think they're very interesting observations. Lots of different explanations for what could cause something like this. I mean, we don't know. And you're absolutely right. It's not included in any of these cartoon type things, like a hybrid type model, or like a messy convection from upper to lower, where it happens in some places but not so well in others. So I absolutely agree.
I think you make a good point, Adam, in the sense that the longer these slabs hang out in the mid-mantle warming up, the less able they're going to be able to draw heat out of the core when they finally do get to the bottom. It's a fair point.
I have a question regarding that. How long, on an Earth time scale, I mean, how long, based on dynamic models, would these slabs be stagnant for? I mean, because you're saying that in your models they're only stagnant for a short amount of time. But what is that on geo time scale?
Good question. I'm just going to throw a number out there, like tens of millions of years, but I don't know. I say that number based on my memory of how long it was, and with respect to how like a convection cycle lifetime. So tens of millions. Now, just because that shows up in a model, like I see things like this in a model, that doesn't mean that's what's happening in reality. I'm just saying it's something that can occur. And usually this is the result of, it can occur for different reasons. One is if this downwelling area is retreating, because viscosity is higher, well, at least in models we make viscosity higher in the lower mantle because we think it is. So if you have the downwelling is retreating, it's going to look like it's laying on top of the lower mantle. It's just slowing down. It's not really laying there. Another way that can happen is if something else is going on further away that's controlling the pressure field. So we often forget about pressure field when we're interpreting things. So in the fluid dynamics, the buoyancy field, so cold things sink, hot things go up, but those create a pressure that affect other things. So if you have strong things happening in a distance, they can affect smaller things happening over here. And so another time that shows up is if the pressure field can push a region or create a mantle wind, is another way to think about it, in a region, and that can cause slabs to be deflected, and plumes. Yeah, and plumes. It does that to plumes too. So that's another time it shows up in convection models. Now again, that doesn't mean that's what's happening on the Earth. Yeah, thanks. Thank you.